This is a tutorial on stoichiometry, and we're going to look at converting particles of A to moles of A, where A can be any substance, it can be a pure element, it can be a compound, it can be any type of compound that we see in inorganic chemistry. So in stoichiometry, we're trying to calculate different quantities in order to get other results. In this case, again, converting from particles of A into moles of A. So what we have to remember here is Avogadro's number, and Avogadro's number is quite important in inorganic chemistry, especially when we're talking about stoichiometry. And we need to know that Avogadro's number is a counting unit. It's like saying a dozen. So a dozen is equal to 12 units of anything, right? So a dozen watermelons, a dozen apples, a dozen grapes, etc. But Avogadro's number is equivalent to 6.022 times 10 to the 23rd, so that's a huge number of atoms or molecules. Okay? So in this case, Avogadro's number is also what it basically means is this is the amount of atoms or molecules contained in 1 mole. So 1 mole has this many particles, so it can always be expressed as a conversion factor. Now, if we take this into consideration, particles A to moles A problem involve the same substance, where the initial setup is very simple. We have our particles of A over 1, expressed algebraically so that we don't modify it, where the next number is Avogadro's number expressed as a conversion factor, where what we want to cancel is X particles of A in 1 mole. But this is an X. This is actually Avogadro's number, 6.022 times 10 to the 23rd atoms or particles. And here we have the given quantity. So we're only going to need to punch this into our calculator, and we're going to get a result where particles cancels out, and we're going to get our result in moles. So a amount of moles. Okay? So this is better explained with a very simple problem. We can do how many moles are found in 2.41 times 10 to the 24th molecules of water. So here water is just given as an illustrative example, but it's not something that we really need to know to work this problem. And again, how I showed you in this, we just need to set up these two, where first we have our given. Our given is 2.41 times 10 to the 24th molecules of water. So I set up my first factor, 2.41 times 10 to the 24 molecules of water over 1, so that we don't alter it algebraically. And then we want to write Avogadro's number as a conversion factor, where we know that 6.022 times 10 to the 23rd molecules of water is equal to what? 1 mole of water. So what's going to happen here is molecules of water is going to cancel out, and we just punch this into our calculator really quickly. 2.41 times 10 to the 24th and times 1 divided by Avogadro's number. So the method we're using here is actually dimensional analysis, which might be kind of long for certain students, but it's a good foolproof method so that we know what units we're getting, okay? So in this case, my answer is 4.00199, and in this case, what survived was moles of water. But it depends on what your teacher asks you for. I always ask my students to round to 2 decimals. So my complete answer and my final answer that I would box is 4 moles of water, because this 1 won't round up, so 4.00, 4 moles of water is the answer. Next, let's do another problem. In this case, it says how many moles are equivalent to 800 atoms of gold. So you can imagine 800 atoms of gold is a very small quantity, considering that 1 mole of anything has 6.022 times 10 to the 23rd molecules or atoms of anything. So we're going to get a very, very small number. So mind your scientific notation. My first setup is I'm going to write my quantity, which is my given. So I have 800 atoms of gold over 1, so I don't change it algebraically. And my next factor is, again, Avogadro's number, 6.022 times 10 to the 23rd atoms of gold is equivalent to what? To 1 mole of gold. So, once again, atoms of gold is going to cancel out, and what we get is, again, a division. 800 divided by Avogadro's number, 6.022 times 10 to the 23rd, and my answer rounded up is going to be 1.33 times 10 to the I think I made a mistake here with my calculator, so let me check what's going on. 1.22. I'm going to try this again. Yes, so 1.33 times 10 to the negative 21 atoms, not atoms, I'm sorry, moles of gold. And this is my answer. This answer makes sense because 800 atoms is very little, so we're expected to get a negative exponential number in the scientific notation, and it's this simple. So basically what we're doing is to convert, we're dividing the particles by Avogadro's number, and we're getting an amount of moles. But with dimensional analysis, we do the setup, we see that the units cancel out, and my final answer is moles of gold.